Let's go over the module operator, or mod for short. The majority of this comes from the idea that the remainder of a divided by b is r. This can be expressed in multiple ways. One such way is a equals kb plus r for some k in the integers. This fancy z meaning integers like -1, 0, 1, ... and also negative. A third statement would also be b divides a minus r, where if I take the r on this equation and I move it over to the other side, you can see that that left side is now divisible by k times b. Here's where we introduce the module operator. A fourth way to express this is a mod b equals r. This is just a shorthand way of saying the other three things that we just discovered. Likewise, the fifth way of doing it is that a is equivalent, this symbol, to r modulo b. You might see this one more often than the one before, but both of them are equally valid. After familiarizing yourself with that notation, you might be presented with something like this. What if x is equivalent to 0 modulo y? This also means that the remainder of x divided by y is 0. X is a multiple of y, and there exists an integer k such that x equals ky. An example of this is that 10 is equivalent to 0 mod 5. To repeat these three bullet points using our example, the remainder of 10 divided by 5 is 0. 10 is a multiple of 5. And there exists an integer k, in this case k equals 2, such that 10 equals 2 times 5. There are other operators, most of them having the same principle. If I have x plus y modulo a, I can split this up and take the remainder as I go. I can take the remainder of x, take the remainder of y, add them together, and then take the remainder again. This might seem a bit redundant, but it has some useful properties. Let's go back to another example. Recall from earlier that a, or any multiple of a, is equivalent to 0 mod a. In other words, if I have 5, or any multiple of 5, and I divide it by 5, it has a remainder of 0. This is because 5 always divides itself. Using this fact, what if I add x to one side? Well, I can split this up. I can take x, and I can take k times a, and I apply mod a to both sides. Mod a of k of a is just 0. If I apply mod a to x, we don't know what that is, and therefore, we'll just put it on the other side. This simplifies down to x plus k times a is just x mod a, using this principle above. Here's a numerical example, just like we did on the previous slide. 2 times 5 is always 0 mod 5. Therefore, if I have 3 plus 10 mod 5, this is equivalent to just 3. Because 10 is a multiple of 5. This same principle applies to multiplication. If I have x times y modulo a, then I could split the x and the y, take the remainders separately, and then multiply the remainders together, and take mod a after that. Here's a bigger example. What if I asked you to find the remainder of 13 to the power of 71 when divided by 5? I'll show you two methods to do this. The first step of this first method is converting 13 to 3 modulo 5. We can do this because 13 is equal to 10 plus 3, and 10 is a multiple of 5. Next, recall that 3 squared is equal to 9. And then 9 is equivalent to -1 modulo 5. This one might be tricky, but notice that I can have 9 subtract 10, and I will get -1. Since 10 is a multiple of 5, these two statements are equivalent modulo 5. Next, we can rewrite the original statement, split up the power of 71 into 70 and just 1 by itself. Here's 70 and 13 to the power of 1. Notice that I separated 13 squared. This will be useful because we can rewrite this as -1 to the power of 35 times just 3. I'm using one of the rules up here. I take 13 equivalent to 3 mod 5, and then I take 3 squared equivalent to 9, or just -1 mod 5. This is to say, 13 squared is equivalent to -1 mod 5. Therefore, this 13 squared can be rewritten as -1, and this 13 over here can be rewritten as 3 mod 5. After that, -1 to the power of 35 is still -1, and what we're left with is -1 times the remaining 3, or just -3 mod 5. negative 3 is also equivalent to negative 3 plus any multiple of 5 when it's mod 5. Therefore, I can add 5 to negative 3, and this can be rewritten as 2 mod 5. Another example is very similar. Repeat the steps 1 and 2. As a third step, let's cube 3 instead of square it. This gives us 3 cubed, which is equal to 27, which is equivalent to 2 mod 5. Notice that I can take away a multiple of 5, 25, from 27, which just gives us 2 left over. That is to say, this step tells us that 13 cubed is equivalent to 2 mod 5. We will use that in the same way. Rewrite the powers of 71 as 13 cubed to the power of 23 times another power of 2. Next, we use the fact from up here to rewrite 13 cubed as just 2 modulo 5 and 13 squared as negative 1. Another intermediate step is to use 2 to the 4th, which is 16. We can separate 16 into 15 plus 1, and therefore 16 is equivalent to 1 modulo 5. This allows us to split up that 2 to the 23rd power into just 2 cubed times 2 to the 20th, which is divisible by 2 to the 4th, are just 1 modulo 5. 2 to the 3rd is 8 times negative 1 gives us negative 8. The last step is that we can add a multiple of 5 to negative 8, which just gives us 2 modulo 5. These two methods lead to the same answer, but take different approaches, and neither one of them is necessarily the best method. Play around with these methods. Use bigger powers or different divisors. You'll find your own approach to solving these modulo problems. In any case, I hope this serves as a nice introduction. Please subscribe if you'd like to, and thank you very much.